So we had 8 H's there, so 8 H pluses were brought in there. And we have, what, 6 H's here, so 6 H pluses came in there. That's good. Okay, Peter Fusina, what do we balance after that? Just keep in mind, this is 6. Charges using electrons. So would you do that for the first one? The oxidation reaction? And Bo, would you do that for the second one? So the reason I said that, now if this were basic, wouldn't we, before we do electrons, have to do something else? What would we do? Bring in OH. So how many OHs and where?
The same amount of H's and
Same amount of H pluses and add it to both sides. Good.
So we take, so for the left side, we take 8 OHs.
And add it to both sides. If this were basic. And then we go back to the chart.
Skip that step into decision. Gotcha.
Okay, I think we've got a problem there here. All right, so what we're trying to do is get both sides equal. Okay, we're not worried about neutral. We just want them to be equal. So initially you have 2 pluses here. You have 8 pluses there and 1 minus. So this side is +7, this side is +2. And we want to get them to be the same. And when you add electrons, all you can do is bring a side down. So we want to go to the larger side and bring it down to the smaller side. Okay, so we get the charge, and up here we have 2 positives, so this whole side is +2. There's a negative and 8 positives, so that's 7 positives over here. So I'm going to bring +7 down to +2 by adding 5 electrons here. So now this comes out to be negative 8 positives, that's +7, minus 5, that's +2. Over here, test my eyes, man. 6 positives here. 3 positives and 1 positive. So this side's +4, this guy's +6, so we're going to add 2 here to bring that down. Okay. Alrighty. Tyler McKinney, what do we do next? So what's going to be a common number for these 2 equations here? 10. So will you get that to be 10? And we have Jake Emerson come up and get this one to be 10. And I don't know. You guys can decide. One of you guys can write your equation right underneath, and maybe one of you guys write your other equation underneath that one. And you can do it either way.
So how'd you get the electrons again?
For both or for one?
Just one.
Okay. So, well, let's wait until we can see. How many of you guys watch the game? I didn't watch it, but I heard what I heard. It was pretty exciting. Yeah. Whoever would have thought that Clemson would win that? I heard people talking smack on Clemson all day yesterday. I'm like, I don't know. I don't.
Did Jack Day go to Clemson?
Yes.
Good for him.
Yep. He's probably having a good time.
I'm sure he is.
I mean, I would imagine that the campus is just going so crazy. So let's look at both of these on how we get charges before we multiply. Okay, so going back to this line right here, this is one we just got done adding our H pluses, we got to figure out charge. So there's 2 positives on the reactant side. On this side, there's a negative, and there's 8 positives. So this side is +7, this side is +2. I've got to add electrons to balance charge, so that's going to bring the overall charge down. So if I add 5 electrons here, I bring this what was +7 down to +2. And same thing over here. Back at this step was when we, let's see, yeah, right here, we had 6 H pluses, so 6 positives. Here we have 3 positive and 1 positive, so that's 4 positives. I'm going to bring 6 positives down to 4 positive by adding 2 electrons. Making sense? So now we decided the common number, since this was 2 electrons and this was 5, would be 10. So we multiply this equation by 5, so 2 becomes 10, 5 becomes 30, 5 becomes 5, 5 times 1 becomes 5, 5 times 1 becomes 5, 5 times 1 becomes 5, 5 times 3 becomes 15. And then Tyler took his and he said 2 times 4 H2Os is going to be 8 H2Os. 2 times Mn plus 2 should be, oh, it's okay, 2Mn, right? So you just missed it there. It was just like a hiccup, right? So he caught it here, 2 Mn's, 16 H's, 10 of that. And I'd say that that's probably the most common kind of mistakes that happen in these problems. It's not like you don't know it. It's just there's so many little pieces. So all I'm saying is take your time. Take your time. The neater you are at stacking things, the better it'll go. Okay, now Garrett, before we combine these things, those are 2 half equations right here. So we're going to probably put a line under the plus sign. Let's cancel away all that we can cancel away. And here it turns out to be quite a few things to cancel away. Good job.
Is that it?
I think that's it, yep. Okay, so let's look here. So Garrett hit on the electrons had to cancel first, right? That's got to happen, right? Well, if the electrons don't go, you're screwing up someplace. Then he said, I've got 8 waters here and 15 waters here. So all 8 of those waters go away, leaving 7 waters here, which you wrote up above. Then you notice he had 16 protons or hydrogens here and 30 here. So all 16 of these go, leaving 14 of those. Okay. So Trent, would you come up and tell us what the result of all that is? Trent says we have 14 H pluses coming from here, that's good. 5 NaBiO3 there. Those are all gone, those are all gone. 2 Mn plus 2, that's good. And over here, he's saying we got 5 Bi plus 3, 2 MnO4, 5 Na plus, and 7 H2O. Okay, so let's see, does that make sense? It does. Now, so what do we get here? We get 14 H's here, 14 H's there, 7 times 2. 5 sodium, 5 sodium, 5 bismuth, 5 bismuth, 15 oxygens, 8 oxygens, plus 7 more is 15, 2 manganese, 2 manganese, 14 positives, and 4 more positives is 18 positive on this side. So this side better be 18 positive. There's 15 positives. There's 20 positives, minus 2, 18 positives, that works out. Okay. We try another one, and then if we get up to the bell, we'll put it this way. How about this? We'll have you guys do another one, and I got to recognize what the agents are. But because I know if we go at this pace, we're not going to finish. How about we do the basic one all the way up to the point of the OHs, and then I'll take over and finish it from there, because I think that's repetitive. Does that make sense? Okay. All right, so for this one, this would be, let's see, this is oxidation here. So this is the oxidizing agent. Because this thing causes that thing to be oxidized. And this thing is the reducing agent. Because this thing's causing that thing to be reduced. Right? Now keep this in mind if you look in your notes. The whole substance is the agent. What's being oxidized and reduced is just a particular element. Right? That's in your notes.
What kind of like reactions would these look like?
Some of them, they vary. Some of them look like fire, like something burning. Some of them look like something rusting, just slow. So what do they look like? It depends on the speed at which they react and what substance they're reacting. So they're not necessarily going to look a lot different than any other reaction necessarily, but they can. Let's put it that way. Okay, so let's look at another one here. Anybody need time with this? Good. Okay. This would be 70